Okay, good morning everyone again, and welcome to the second talk of the morning session. So Professor Jörg Wrachtrup from University of Stuttgart and Max Planck Institute will be sharing his second talk with us. Professor Wrachtrup, the floor is all yours. Thank you.
All right. Good morning, everyone. Happy to see you again. And I'll continue along the lines I was introducing or starting to do on Monday. So I might jump off for a few seconds because we had a very hot day yesterday, like 37 degrees Celsius, and now it's colder. I opened all windows, but a thunderstorm is pulling up. So I might be, might jump off my chair and might need to close the windows at some point. Anyway, once again, I'm happy to continue what I did on Monday. And specifically today, I would like to give you a bit more introduction into the application of quantum sensing. We are going to some very specific examples which show you where the highlights, the pros, but also limitations of what we are doing is in. And then I'm giving you a brief introduction what we do in quantum computing, and I see there is a typo here on my title slide. All right, so without further ado, as we are pulling late anyway, let me pick up or start where I ended last time. So on Monday, I was telling you how we use multiple qubits for quantum sensing to enhance spectral resolution. And the story was so that the sensor we are using in our system is an electron spin. This is the first line you see here. And typically when we start quantum sensing, we initialize the sensor into one of its spin eigenstates, say 0. Because of the limited spin relaxation time of the electron spin and also its dephasing time, we use a second qubit, which is a nuclear spin, which is hyperfine coupled to the electron spin. So there is a mutual interaction. And what we do is, in order to enhance spectral resolution, is we generate an entangled state between electron and nuclear spin. That's what you see here. We then let this electron and nuclear spin entangled state evolve, say, in an external magnetic field. So this 1-1 state is acquiring a phase phi compared to the 0-0 state, which has no magnetic moment in this description. And then with a final gate here, we disentangle the two. So we then essentially store the phase we have acquired here into our memory qubit. All right, so this phi now is in the memory qubit. Nuclear spins do have minute relaxation time, even under ambient conditions. So we can store that for a very long time, capital T. And then what we do is we essentially, once again, do this entanglement-disentanglement sequence. And by this, at the end of this pulse, we have stored the phase difference, delta phi, which occurred between this time here, so capital T being 0, and capital T being capital T. Right, and it is this phase difference, which then is the result of our quantum measurement. And we can measure this delta phi in the nuclear spin over a minute, and 1 over a minute gives you the spectral resolution, which then is on the order of a few hertz. And this is what we were applying to measure the nuclear magnetic resonance signal, or which we were applying to measure the Larmor precession frequency of different nuclear spins. And in this case, these nuclear spins were fluorine, which were at different parts of a molecule and thus experienced a slightly different local magnetic field. And that's what you see here. So this frequency axis here is on the order of 500 hertz. And you see the two lines. The line width is on the order of 200 hertz or so, or 180 hertz, and you can see them well separated. If you would not use this quantum memory trick, our spectral resolution would be a kilohertz, and we only would see one big line. This is where I ended up in my last presentation on Monday. And then I made a remark, and I would like to go into the details of this remark. This is how I want to start today or this morning. What happens if you not only use one memory qubit, but if you use multiple memory qubits? And the gate sequence we are running, so I'm using the language of quantum information here to explain what we are doing, are conditional rotations. So I conditionally rotate the quantum state of this memory quantum bit by an angle phi1 around its z-axis, depending on the state of the sensor. This is essentially what I was doing in the previous scheme you have seen. But I was doing it for a single nuclear spin. Now you can do this for multiple nuclear spins. We have up to 10 memory qubits we can selectively address. And I'm doing this for a different rotation angle phi as a controlled rotation gate. Once again, I control what I'm doing on the nuclear spin by the sensor electron spin quantum state. And I can repeat the same scheme for the memory qubit 3 and also the memory qubit 4 and so on and so forth. And depending on whether you had your quantum info lecture or not, or if you had it and or if you were reading a book, you will see that this kind of gate sequence, controlled phase gate with different phases, phi1 to phi4, that is actually nothing but the gate sequence of a quantum Fourier transformation. You see, this is the same type of sequence I see here. This R, this pi over 2 to the power of n minus 1. This is exactly these different angles, phi1, phi2, phi3, phi4. And you apply this in a systematic way. And this by this, you actually generate a Fourier transformation of an incoming signal or wave function. All right, and I want to show you how we implement this in our scheme. So the way we do it is we take 3 nuclear spin quantum memories, M1, M2, M3. We prepare them in the right state. Then we apply these conditional rotations. So we conditionally rotate in this case, the electron spin on the state of the nuclear spin quantum memory. And these U1, U2, U4 are these rotations around the angle phi1, phi2, phi3. Rotation axis is the z-axis. And in the end, we do a readout of these 3 nuclear spins, right? We can selectively read them out. I will explain you later when we come to quantum computing how we do this. And by this, we want to actually measure a signal. So this is the signal we want to measure, which contains more than one frequency, right? So it's not just a sine wave, but it's a mixture of sine waves. And we want to measure this in a single run. And this is, well, this is essentially the result of it. So if we apply this quantum Fourier algorithm, and if we read out the individual memory qubits, qubit 1, 2, and 3, then we can digitize the phase we are measuring. So this is the phase we are measuring, and this is the bit values we are getting because of that readout, right? Remember, we do a quantum Fourier transformation. So essentially, you digitize the phase you are looking at. And these are now the bit values, 0, 0, 0 for the 3 qubits, 0, 0, 1, and so on and so forth. Okay. And this is what you expect in theory when you actually do a simulation of the algorithm, and this is what you expect in experiment. So by using the quantum Fourier transformation, what you get is an easy readable and unambiguous digitization of the phase, right? So if you have never looked into the quantum Fourier transformation in classical quantum computing, this is the way, and this is the value of this algorithm. Just for a comparison, you do not need to apply the quantum Fourier transformation to measure phases. That's obvious, right? You can do this with any kind of other gate sequence. And one way actually to measure phases would be a Hadamard gate. A Hadamard gate is if you say take the spin analog of a quantum bit and you say in the beginning of the experiment the spin is pointing towards a positive z direction, say this is a logical 0, then a Hadamard gate essentially is turning that spin by 90 degrees and generating coherent superposition between 0 and 1. And this coherent superposition of your memory qubits is now evolving in the external magnetic field, and you acquire a phase. And now you can, that's exactly the gate sequence. And this also allows you to measure a phase. And if you read out your 3 nuclear spins, you also get a digitization of the phase. So that's the same x-axis here. And once again, we read out the bit values. And once again, for a phase value, say phi equals 0, you get a specific bit value. However, because you have not applied the quantum Fourier transformation, you do not have an unambiguous digitization of phase, right? You see this 0, 0 here gives you 2 phase values, 0, 0, 1. Also, you have 2 phase values, and so on and so forth. So, and while this is a theory here, this is once again an experiment. So the takeaway message here is the benefit of applying this sequence of controlled phase gates in your multi-qubit system is that you get a unambiguous digitization of the phase. This is actually the virtue. This is the function of the quantum Fourier transformation. All right. I'm just showing you the example we were having. So this is actually the periodic signal we were having in our system, right? And we were this is this is the periodic signal. One of the memory qubits is recording. This is the signal the other memory qubit was actually recording. And if you now do the Fourier transformation, you see that these are 2 essentially sine waves with 2 different frequencies. And by actually taking these different memory qubits, you can disentangle these 2 sequences while you are measuring it in one experimental run. All right, so this is probably a plot which most of you have seen multiple times during this conference already. And now I'm interested in actually how does the precision scale by which I can measure actually my phases. And for this, I plot the Fisher information of my phase measurement as a number of qubits involved. And as usual, I take the Heisenberg limit as one limitation of precision scaling, and I take the standard quantum limit, this is this orange curve here, as another benchmark precision scaling in the experiment. And what I see is that if I apply this quantum Fourier transformation type of phase measurement in signals where I have multiple frequency components, then this scales somehow in between the standard quantum limit and the quantum Fourier transformation. So this curve here, this light blue greenish curve is actually what you get as from a calculation when you analyze the experiment, and these red triangles is what we are measuring in experiment. So overall, this algorithm we are using improves Fisher information scaling of the recording of these signals above the standard quantum limit. We do not reach Heisenberg limit, although we are using an entangled state. And the reason is that there is a certain computational overhead to do the quantum Fourier transformation, and it's inverse in the end to read out the signal. All right. So this is actually the way how these days we measure periodic signals which have multiple frequency components. So all our nuclear magnetic resonance experiments are done essentially in this way. From the application point of view, being able to image signals is an important characteristics, right? So we not only want to measure some kind of phase information, that is periodicity of an oscillating signal, but we also want to spatially resolve these experiments. And there are different ways of doing it, and I'm showing you one way of doing it, which is actually done by these two gentlemen here. We call this Widefield NMR imaging, and I guess it's fairly easy to see how we do this, and you come up with quite an interesting result if you do that. What we do is actually, the overall setup very much looks like a conventional optical microscope. You have a laser for excitation, you have a microscope objective to focus and achieve diffraction limited resolution, as you will see, and you have a detector. This blue thing here is a specimen, and this gray thing with the thin red line, this is a diamond chip in which we have generated a thin layer of NV centers, of these magnetically sensitive sensors close to the chip surface. And these NV centers actually, they record the local magnetic field of the sample and convert it into fluorescence intensity changes, and this is what we detect. So in a nutshell, the central part of the overall imaging device looks like this. You have your microscope objective, you have a detector, which is a CCD, you have your layer of dopants, diamond dopants. The fluorescence intensity of these dopants, these NV centers, depends on the local magnetic field of the specimen on top of the chip, and they convert actually this local magnetic field into a local fluorescence intensity, which you measure then on your chip. This is essentially how this works. And we were actually now doing experiments on demonstration experiments, showing on the one hand the recording of this periodic and multiple frequency periodic signals, which are actually the Larmor frequencies of nuclear spins, magnetic nuclear spins, plus imaging. Right, that was the idea of it, and we were taking a very specific sample, which is a cell. So this is a biological cell. It is a HeLa cell, which is a human cell. It has a cell membrane. It has a cell nucleus. Typical diameter of this thing here is on the order of 50 micrometer or so. And we were taking this example because the cell contains specific nuclear spins, that is nuclear spins with a specific Larmor frequency at different parts of the cell. And specifically in the cell membrane, you find these molecules, which are phospholipids, the bilayer of which actually constitutes the cell membrane. And there is one specific nucleus, phosphorus 31, which has a very distinct Larmor frequency in due to its nuclear gyromagnetic G value, which is distinct from all the other nuclear spins, which mostly is carbon-13 and protons. And we want to measure this signal to localize actually the cell membrane. An experimental example you see down here, this is actually what we call it bright field image. That's a standard optical image. Some of you might have taken yourself when you were in school or at university in some bio classes or biochemical analytics classes. And this now in comparison is our MRI image, and it is a fluorescence image. So you can specifically label this cell membrane with a dye, which is emitting light at a very specific wavelength. And by this, and this is the standard method, you can make these cell membrane lightening up. That's what you see here. And this here is the MRI image. It's called relaxation image for reasons I will tell you later on. So, and you see it follows roughly the shape of this stained cell membrane. So I guess there is good reason to claim that this really is a cell membrane, just taken from the nuclear magnetic resonance signal, or from the LAMOR signal, the periodically modulated magnetic field signal of the cell membrane. So signal to noise, of course, here is bad. It's probably as bad as it is in the fluorescence image. But the advantage of these MRI images here is that you do not need any staining. So you do not need these dye molecules, and these dye molecules often interfere with biofunction, and you don't want to have them. So this is the first kind of these type of measurements. Signal to noise, once again, is bad, but I like to compare it to this image here, what you see on the top right corner. This is taken more than 40 years ago, and it is the first magnetic resonance image. So it's the first MRI image ever being taken. You see signal to noise is similar, even the shape is similar, although this is a coincidence. What you see here is a cut through the human body on the height of the belly. The overall dimension here is roughly 0.5 meter, and here it is roughly 20 micrometer or so. That's the length scale. And if you see what after 40 years of development have come out of these images, right? How much better they got. MRI these days is the #1 medical analytics technique to measure soft tissue in hospitals. So if our technique undergoes the same type of development, it really promises to have a huge impact, if not a revolution, in cellular microscopy. All right. So what is it, just as an outlook, what is it we can do with this? Well, on the one hand, we can very efficiently now measure multiple frequencies in an almost optimum sensitivity scaling. On the other hand, we can also image where these signals are coming from. And the big dream here is to be able actually to see into biological cells like the one I've shown you here in way more detail without any prior chemical treatment of the cell. For example, it would be fantastic if we would achieve measuring membrane proteins separately from actually the membrane molecules, the phospholipids you have seen, and even tell apart these individual type of proteins we have, which all have different functions. And if you can do this in a live cell context, so in a cell which is actually doing physiological function, this would just be fantastic and for sure enhance our knowledge on these structures very much. So that's one direction where we are developing this into. And the other one is this. So the sensor types we are using actually might lead to radically improved and simplified MRI. MRI, as you know, as I was saying, is probably the most prominent biomedical analytic technique next to X-ray, but it is a bulky experiment, this wide stationary. Our sensors function in such a way that you can make this thing actually radically smaller, probably even make it a handheld device, which like in this mock-up would allow you actually to record at least soft tissue images in these type of devices. And these are the two directions into which these days applied research with these sensors go. All right. So I want to, if we go back 1, 2 slides here, and then this, you see it, I was not labeling it magnetic resonance image, but relaxation image. It's a magnetic resonance image, but taken in a very specific mode. And I would like to explain to you why we call this relaxation image, because there is some intricate physics in this. So let me go back. Okay, so essentially what we do is, in these experiments, if you look into the details of how we record the signal, is we are measuring magnetic noise. So essentially, if you plot the noise power spectral density, S of omega, as a function of frequency, and you put some kind of specimen on top, then what you typically get is this 1/f type of noise, right? You can, besides looking at our experiments as recording the precession, the Lama precession of nuclear spins, you can look at them as actually measuring the magnetic noise from those nuclei. And I would like to go with you through the line of argument you're making there. So essentially, you are taking a molecule which contains magnetic species, electron nuclear spins, and these generate magnetic noise, and you take your ND center being a detector. And then you try to measure this noise power spectral density. All right. Say you have a specific nuclear spin, for example, this nitrogen here, which can be nitrogen 15, nitrogen 14, both of them have a nuclear magnetic moment, and so they generate a periodical modulated magnetic field with a specific frequency, which we call Lama frequency. And by this, we chemically identify the specific nuclear spin. All right. So what we want to measure now is exactly this noise power spectral density. And typically, we employ different control sequences on our electron spin to measure the different frequency ranges in this noise power spectral density. If you now closely look at this, the noise coming from the sample, then we have this 1/f noise, and we have a peak, a noise peak at certain frequencies, which actually come from the Lama frequency, the magnetically modulated signal from the nuclei we want to look at, right? And of course, we exactly know where this is because we know the nuclear G factor or the gamma, for example, of carbon-13. And now we want to isolate this peak, this noise peak, right, from the rest of the noise, magnetic noise coming from the sample. And the question is how we do this. This is another way of looking at the experiments we are doing. And I was already making this analogy once. A very efficient way of exactly isolating a certain frequency component from a broad spectrum of signals you get is actually using a local oscillator, like you are using in your old analog radio receivers, and demodulate the signal at exactly a given frequency, say FL here. Now, how do we generate this local oscillator in our experiments? And I'm giving you now an example or a couple of examples showing you how we do this. Typically, what we do is when we measure our signals is we apply a sequences of pulses to the sensor space. And the sequences of pulses, that's the argument, is actually generating a filter function. And this filter function selects out specific noise components from our signal. Now, in a more formal way, if we take our, say, if we take the signal from our sensor spin, we call it C of t, then actually this C of t, this signal, this the signal of our electron spin, after I have initialized my electron spin, decays as a function of time. And if we are measuring the coherence of the electron spin, and this is what we are doing, then actually this decay is governed by the phase fluctuation of the electron spin. So what I'm discussing here are, for example, experiments like this one, where you apply a pulse sequence, you apply a pi/2 pulse to your electron spin, you apply a pi pulse and a pi/2 pulse. This is what is called Hahn echo. And by this Hahn echo, you measure the lifetime of the phase of the wave function of the electron spin. And this, the phase of actually your electron spin decays as a function of t and of time. And this is just the average, you know, of all the different frequencies your electron spin has as a function of time. You can actually write down a function theta of t, which describes this loss of phase information of your electron spin, of your sensor electron spin. And this theta of t is nothing but the integral over the noise your electron spin is exposed to. So it's noise power spectral density S of omega times a filter function. And this filter function is determined by the pulse sequence you're applying. All right. So now so if this is the noise spectrum, let's look at different filter functions, which essentially, and this is a very simple way to look at these filter functions, they are a Fourier transformation of the pulse sequence you apply to your electron spin. Well, and if you take the Fourier transformation of such a sequence of pulses, which is pi over 2, pi over 2, pi over 2, and so on and so forth, then the filter function is this periodically oscillating function where the frequencies of maximum transmission are these peaks here, whereas 0 means that the filter function actually is eliminating or suppressing the incoming noise signal very much. So this is how it looks like with the Hahn echo. If you apply not one of these inversion pulses on your electron spin, but a whole sequence, say of n pulses, then your filter function changes and it gets less peaks, which have a higher transmission. So the suppression ratio between not transmitting the signal, blocking the signal, and receiving the signal is getting way higher, right? So this is a quantitative measure. So by applying a large number of these pulses, you can actually generate filter functions for noise, which have a rather narrow frequency band and which have a high dynamic range. And this is how we actually measure these noise peaks. Because if I change the pulse spacing here, I change the frequency at which this filter function is getting transmissive. And by this, I can scan my S of omega noise spectrum. All right. So let's see how we actually do the experiment. And a rough sketch is shown down here. I guess we don't need to go into the details. The important thing is that this block of orange squares is actually a sequence of these pi pulses, the Fourier transformation of which constitute this filter function. And here, this is essentially the contrast you see in your noise measured signal. Now, say we have a certain spacing of these pulses with a certain value of tau, then I have a filter function which is transmissive exactly at the frequency tau, which is tau lambda over 2. Okay. Now I increase my tau, so I increase the pulse spacing, right? For example, such that the tau, so tau lambda is the lambda frequency of the nuclear spin I want to detect. Okay, so if my spacing tau is way longer than this lambda frequency, then in my signal recording, I'm here where this bluish dot is. If I now further on increase the pulse spacing, so that actually my tau is exactly commensurate with the oscillating signal I'm measuring. So this is a lambda precession signal I'm measuring. Then my filter function is maximally transmissive, so I record the signal. And now if my pulse spacing is too large, right, so that I'm not commensurate anymore with this periodic oscillation of the lambda precession of the nuclear spin, once again, my filter function is shutting off that signal. So what I want to say is here is actually that this description of incoherent noise and coherent periodic oscillation is somehow are two sides of the medal, right? You can look at it in the noise way, or you can look at it in a way of a coherent, phase stable oscillation. Okay, so here you see an experimental example. So this is a measurement signal, and you see what I'm doing here is I'm changing tau and I'm scanning over this peak here of my noise spectrum. And you see that when my tau is exactly the lambda precession period tau L over 2, I see a dip actually in the coherent signal of my electron sensor spin. And this is essentially my signal. There is a certain scaling of the filter function amplitude and width with the number of pulses we don't need to be interested in. But essentially what you measure here is the phase coherence of your electron spin. And when you are in measuring the, when this phase coherence time hits a certain point where your pulse spacing of the pulses you treat your electron spin with is exactly commensurate with the nuclear spin Lama precision, you see a dip in coherence. All right. This is not a long time back that we were doing first experiments, and by this, that is the gist. You can measure actually the signal of nuclear spins, carbon-30 nuclear spins at some nanometer distance. So the fields we are measuring here approach sub-nanotesla field amplitudes, and we have this just tells you here that we are able to measure nuclear spins at different frequencies. So this is the Lama precession frequency over the signal intensity, and you see here this is on the order of a kilohertz, and this is on the order of 500 hertz or so. And the dip here actually is a dip in the electron spin coherence. So what this says is that this Lama precession of the nuclear spin is actually maximally decohering your electron spin. All right. Now, once in a while, you see the following thing. So what I'm plotting here now is coherence of the electron spin, where I say maximally coherent is 1, whereas entirely uncoherent is 0. And once in a while, you see nuclear spin signals where the coherence in this plot is getting negative. We call this quantum decoherence, but essentially what that means is that for certain nuclear spins, which have a large enough signal, long enough coherent precession time, and strong enough coupling to the electron spin, you cannot look at this whole system as being a coherent sensor system and an incoherent noise source, but as a matter of fact, your noise source and your sensor signal, the electron spin, are getting entangled. And because of that entanglement, you see that the coherence, coherent evolution of the electron spin is undergoing a sign change. That is what this is saying. This is why we distinct here the classical coherence, where you have an exponentially decaying function over the expectation value of a Hamiltonian, which is the Hamiltonian of your electron, combined electron nuclear spin system. Well, in this quantum correlated state, in this entangled state, a type of sensing situation, you also have quantum back action. That is when your electron spin is measuring, and when you measure the phase on your electron spin, you see that it has a back action on the nuclear spin, and this you can see here by the slightly different frequencies we measure upon different measurement sequences of the electron spin. So this red curve here is one way to measure the electron spin. The blue curve is a signal when you have another way of measuring the electron spin, and you see it's slightly distinct frequencies. This comes from the back action of the electron spin, and that's good confirmation that at least in this case you have an entangled electron nuclear spin system. All right, the point I would like to make here is that over the last 10 years, people have made this a piece of art, and the most recent version of it you find in this paper. This is from Tim Tamanyao's group from Delft. This is such a measurement where you follow the coherent evolution of the electron spin over an extended period of time, in total 200 or almost 300 microseconds. And you see that this decoherence curve, which typically in most textbooks is a flat curve, just a more or less exponentially decaying coherent signal, has a lot of frequency components in it if you carefully look at it with this system. And this here, this middle graph is just a certain cutoff of this upper graph here for the shaded areas, and you can see that there are lots of dips in this coherent, and all of these dips in the coherent come from the coupling to different nuclei with different coupling strengths. And this guy here from the Delft group of Tim Tamanyao, he was able to isolate in total 27 nuclear spins around the electron spin. And that's here a mock-up of the crystal lattice, not very good image quality, but somewhere here in the middle is your electron spin, and all of these yellowish dots here are nuclear spin within the diamond lattice. So what they were using, actually, they were using this sequence, and the idea of these measurements I was highlighting to actually precisely measure the distribution of nuclear spins around their defect center. And well, this is one way, this is, first of all, you can look at it as a specific way of doing MRI. On the other hand, you can look at it as characterizing a small quantum register. And this is what they were doing with this. They were using actually the 20 nuclear spins at quantum bits in quantum algorithms. And I'm going to explain this later on. All right, so what I would like to do is, at this point, go one step ahead to close off all of this electron nuclear spin sensing by showing you that you not only can measure nuclear spins due to their coupling to the electron spin, but you can also what we call polarize nuclear spins. That is, you can change the quantum state of the nuclear spin by actually initializing your electron spin you use for the measurement. And I will describe you the experiment which leads to this observation in the coming 3 or 4 transparencies. So the way the experiment we were doing is the following. You have a piece of diamond, you have your electron spin in here, right? And then you put a drop of a liquid on top. Could also be a solid, but say it's a very simple liquid, which contains hydrogen nuclear spin, so proton spin, okay? And of course, at room temperature, if you do it at room temperature and conventional magnetic fields, the nuclear spins are pointing in all kinds of directions. At least they are quantized along an external magnetic field, but they're pointing up and down because KBT is way larger than any other frequency scale for the nuclear spins here, right? Now, what you can do is, upon optical excitation of the electron spin in your diamond, you spin polarize the electron spin. So another way of saying is you initialize your electron spin into one of its spin sublevels. That is, by optical excitation, you spin align the electron spin. And if you do this in a clever way, the interaction between the electron spin and the nuclear spin lead to a fully polarized ensemble of nuclear spins. So another way of looking at it, you do a heat transfer or an entropy transfer among the nuclear and the electron spin. This reduces the entropy of the nuclear spin system at the expense of the electron spin. And the electron spin you can then reinitialize, that is, you can put the by optical excitation, which means you can put the entropy into the photon band. This is what people call optically induced nuclear spin polarization, and that can be very useful. Let me just show you an experimental result. Okay, so how is it you're doing the experiment? How do you efficiently generate actually this heat transfer or entropy transfer between electron and nuclear spin? Well, the one thing which is standing in your way is that the electron spin and the nuclear spin are living on different energy scales, right? Remember, if you switch on a magnetic field, the electron spin is aligning along that magnetic field, and the Zeeman splitting is given by the electromagnetic moment. Same is true for the nuclear spin. However, the electron and nuclear magnetic moment are different by almost a factor of 1,000. So the electron spin has a way larger delta E than the nuclear spin is. If you now want to exchange energy, and energy conservation applies here, the energy flow between electron and nuclear spin is very, very inefficient, simply because the delta E, the Zeeman splittings are so different. What you need to do is to have an efficient transfer is actually to force the electron and the nuclear spin onto the same energy scale. And the way you do this, that's a trick from quantum optics, you drive the electron spin. So you strongly drive the electron spin. By this, you generate a dress state, which is a new energy scale. And then the electron delta E, the electron spin delta E, is driven by the interaction of the electron spin with the driving field. So you generate a new splitting omega R. And because you can change the amplitude of the driving field independent of the external magnetic field, which is generating the Zeeman splitting of the nuclear spin, you can tune both of them into resonance. And if you do this efficiently, then you generate an efficiently heat or entropy transfer between the two systems. All right, I'm showing you an example of how we do this. So this is an experimental sequence. This is the first part here on the upper panel is a sequence where we polarize the electron spin. So we shine light on it and we put it into one of its quantum state, which means it's always spin on. This is a sequence which actually forces the electron and the nuclear spin onto the same energy scale. And this last part here is a detection sequence. So if I plot now the electron spin signal as a function of interaction time, then if I'm not resonant with my nuclear spins, I see the following decay of the electron spin signal. So you see essentially what I plot here is the electron spin coherence as a function of interaction time. And if I'm not in resonance with the nuclear spin system, I get a certain decay curve here. Decay time is maybe 200 microseconds. And that means there are leakage channels. So the electron spin is losing its coherence or its spin polarization by different channels, right, other than the nuclear spin. But if I design a situation where my electron spin splitting is exactly equivalent to the nuclear spin splitting, so this is what I call on resonance here, you see that this decay is way faster. And the difference between the two curves, I can plot them. This is this blue curve, actually marks the polarization or heat or entropy transfer between electron and nuclear spin. And you see, this is what is happening. The electron spin actually is losing polarization to the nuclear spin system up to a certain point, 150 microseconds or so. And then both channels are decaying, and this is because the electron and the nuclear spin system are coupled to larger heat baths where they lose polarization. But at least for this 150 microseconds or so, you start to polarize the nuclear spin. Physically, that's an interesting mechanism, because you can ask yourself what determines polarization speed and what determines this decay here. But I would spare us all of these considerations and just make the remark that this has enormous potential for application, because in this part of my lecture, I want to stress application. What you can do is you can polarize these nuclear spins by this means, and the mock-up of how this goes is shown here, right? You have, say, an unpolarized liquid like water, where all the proton spins are pointing up and down in a statistically random way. You use your polarizer, that is the interaction with the diamond surface, and by this you polarize your liquid. Typically, the spin relaxation time of protons in liquids is a couple of seconds, between 10 seconds, 30 seconds, and even minutes. So you can take this polarized liquid and then deliver it to a specimen you are interested in. And people have done this, not with liquids, but with gases, right? Where a subject is inhaling hyperpolarized gas into its lung, and then by an MRI machine, you can actually image the lung. If you would not have hyperpolarized gas in the lung, in the specific MRI image, the lung would be dark because it is a low density tissue. You can't image it with a conventional MRI, but if you fill it with hyperpolarized gas, you can image it. And now with this technique, this diamond-based spin polarizer you can hope not only to reach lungs, but also to enhance the sensitivity of MRI in clinical applications significantly, because you not work with thermally polarized proton spin ensembles, but with hyperpolarized spin ensembles. And this would be important for early cancer detection, in increasing imaging speed in MRI, and so on and so forth. And this is what research is now going on. And first products along those lines are about to enter the clinical test phase in the coming 2 years. All right. So with that, I will come to one other application example of precision measurements using the solid-state spin systems, and this is temperature measurement. So how do you do temperature measurement with our quantum sensor? And I'm going to explain you how we do this in a second. So our defects are actually defects in a crystalline lattice, say diamond, silicon carbide, other solids. The spin ground state of our defects is actually a spin triplet. So you have two unpaired electron spins. These two unpaired electron spins do have a mutual interaction. So, right, we have a dipole-dipole interaction. And the size of this dipole-dipole interaction is just the spin wave function averaged over the dipolar interaction Hamiltonian. That is what this integral says. If you change temperature, you change the average distance of the two electron spins, and by this you change this dipole-dipole interaction part. And this dipole-dipole interaction part you can measure just by precision measurement of the splitting of two electron spin states, and that's it, right? So if you do these experiments, and if you change temperature, and if you measure the transition frequency, so this is all done at constant or say zero magnetic field, you see how this resonance frequency bends over, and this is nothing but an indication that this average distance between the two electron spins is changing. And you can do this in a temperature range from 15 Kelvin, so that's temperature here over frequency, and that's once again frequency over temperature, up to 700 Kelvin. So that's really very large temperature range you can apply this to. The shift, by the way, is on the order of 70 kilohertz per Kelvin. Remember, at 1 Gauss, the Zeeman splitting of the electron spin is 2.8 megahertz. So this is a pretty small temperature change, but because you can very precisely measure the transition frequency of the phase, you can measure this. All right. So in order to do precision temperature measurement, we have designed what we call a thermal echo. But as a matter of fact, what this thermal echo does is, if you have a triplet system, you have 3 spin sublevels, 0, -1, +1, and what you want to measure in order to measure this, the average dipole interaction of the two electron spin is a shift of the center of gravity of these two Zeeman levels as compared to the 0 level. And this is what you do with this pulse sequence. Essentially, you generate coherence between -0 and -1, and after some time, you measure coherence, the coherent evolution of the electron spin between 0 and +1. Right, and if you do this with good timing, you can actually measure temperature pretty well. We, for example, were taking very small diamonds onto a cover slip. We were heating the cover slip with a metallic wire so that you get a heat gradient. And then you this is heating, and then you measure the temperature, and this is how it looks like. So here you see the cover slip, here is the heating element, and here is the local temperature we were measuring, right? And the key feature here is the sensitivity, and it's on the order of 0.1 Kelvin per square root of Earth. This, once again, is not a super precise temperature measurement. There are way more precise ways to measure temperature. But if it comes to the volume, this is a super small, few 10 nanometer large temperature sensor. And this you can use to measure local temperatures. And for some application cases, this is very interesting. And one of these application cases I want to show you. Maybe I make the following remark. These experiments here are not calibration free because similar to the G factor of the electron spin in solids, also this dipole-dipole interaction here depends on the number of subtle parameters in the solid, like strain or so. But this is fairly easy to calibrate. So overall, it is well, it's probably fair to say an easy to calibrate temperature sensor, right? And we were using this actually to measure local temperature in cells. Now, some time ago, like 10 years ago, people were speculating about whether there would be temperature differences in cells. And because temperature is a very widely used parameter in biology to characterize exothermic chemical reaction. If you get access to temperature profiles in cells, you get access actually to biochemical processes, and you get a way to locally measure the efficiency of biochemical processes and also their rate. This was the idea. And people were arguing that based on measurements with other local temperature sensors, specifically molecules, they were seeing temperature differences of 2 degrees Celsius in cells. So you activate certain parts of the cell, it undergoes a metabolic process. This locally heats up the cell, and this they were measuring actually with molecular, they call it fluorescent polymeric thermometers, and they were saying they were measuring temperature differences of 2 degrees Celsius. And this is what you see here in these images. So these are actually biological cells, and this is a thermal map. This is a scale. They were measuring, and you see at some parts, you know, you measure between 35 degrees Celsius and 40 degrees Celsius, whereas at other parts you are measuring more like 30 degrees Celsius. So from that, they were concluding that there is huge temperature gradients in cells. And we set out actually to repeat these experiments. And maybe I can just show you the result. So we were taking nanodiamonds and we were putting them into cells. All these red dots you see here is actually places where there are nanodiamonds in the cell. And these green things here, these are mitochondria. Mitochondria are the powerhouses of cells where the biochemical energy is essentially produced, right? And some of these nanodiamonds are close to these powerhouses and others are not. And then we were actually doing temperature measurements on nanodiamonds which are on mitochondria, on these powerhouses where heat is expected to be produced, and on nanodiamonds which are in the cytosol, so where there is no heat source in the vicinity. And what you see is that with our thermometer, you see no temperature difference. And as a matter of fact, if you go to biochemical arguments, this is what you expect. So the first type of experiments you were seeing with this molecular thermometer were just wrong, because you can make very simple arguments. If you want to measure a temperature profile, T of R, when R is the distance to a heat source, then you expect the temperature to decrease by 1 over R, right? This is the specifics of the heat field. It should be proportional to the heat conductivity, and the temperature should, of course, be proportional to the power being generated by your local heat source. And you can go through the numbers, and if you do this, you come up with with the conclusion that if thermodynamics is right and your understanding of the structure of the cell is right, you would not expect any heat temperature difference larger than 1 millikelvin. And this is exactly essentially what we are measuring. And this tells you that this nanoscale measurements are very often prone to artifacts. You need to take great care and a well-designed sensor to avoid these artifacts. And in this case, these nano diamonds are belong to a class of artifact-free nanoscale sensor. All right. Okay, so maybe I jump over this because we are starting already to approach the end of my lecture, and I will give you a brief account on what we are doing in quantum computing before I finish off, and then allow for a bit of discussion. All right, so as you know, there is now a worldwide race for the optimum hardware of quantum computers, and certainly there are leading systems like superconductors, right? There are the big companies actually advocating microwave quantum bits made out of superconductors. To my mind, the best quantum processors these days are either atoms or ions, because they generate the highest fidelity large-scale entangled states. But what I will argue is that at least for certain applications, these dopants in solids, like for example these defect centers in diamonds, may find application in the global race for optimum quantum processors. And I would like to share these arguments with you. All right. So the way we envision our quantum processing unit or quantum register is as follows. So we take actually the electron spin as the dopant as quantum bits or a quantum bus. We generate arrays of closely spaced electron spins in a solid. We use microwaves, that is our spin control for making gates, and we use local readouts to measure individual bits. Now, a key feature here of such an arrangement is actually the average distance between the electron spin. What you want to have is the electron spin to have strong interaction, stronger than the interaction with any other, degree of freedom in the surrounding, like for example, phonons. And this requires you to have a spacing of the electron spins on the order of a few 10 nanometers, say 50 nanometers. Okay. Now, first challenge is actually to make these arrays, and we team up with people from atom optics to make these arrays. Essentially, what we do is, because our quantum bits here actually are these NV centers, we need to spatially produce these arrays, and this we do by shooting in nitrogen ions into diamond with specific ion sources. Actually, we extract these nitrogen ions from ion traps, and Ferdinand Schmidt-Dahler, Mainz University, is an expert on doing this. And then we shoot them into the diamond. You need a certain kinetic energy to put them into the diamond through nano apertures, which we can produce with great precision. And by this, we achieve this kind of spacing. Our processor looks like this. So this is how it looked like, say, 5 years ago. There's a lot of optics here on the table. As you see, this is actually the place where this diamond chip with the quantum bits is in. In the past 5 years, we cleaned this up a bit and put everything into a big box, and the university and the Max Planck Institute were big sponsors of doing so. So what is in this box is a small chip. You see here control lines, electrodes on both sides, and also microwaves, strip lines. That's what you see on the left and the right side. And in the middle of that chip, hard to see, is actually a diamond. And that diamond, in this case, contains a set of 3 by 3 electron spin. So each of these dots here is actually marked the position of a single color center or of a single electron spin. Scale bar here is on the order of 100 nanometers. So the separation here is like 30 nanometers or so. And what you see here, actually the signal is an optical signal. So we use optical super resolution techniques to actually measure the location of each of these color centers with a precision on the order of 10 nanometers. Okay. So one feature of this array, or one thing you want to demonstrate is that you can measure, you can make these entangled states. Like for example, this belt state, which is a maximally entangled state. Both spins are pointing upwards or they are pointing downwards, but the two spins of say these two color centers here always point in the same direction. That's essentially what this state is saying. And well, then a figure of merit is a tomogram, where you actually measure this state by measuring its density matrix. And well, the tomogram of this state here, you expect to see diagonal elements on the plus plus and on the minus minus element, but you also expect to see coherences between the plus plus and the minus minus. So you also expect peaks here at the off diagonal, and that is what you see. And of course, there is imprecision when you make these states, and this is why all the other elements are non-zero, some of them, and this is also why you do not reach 0.5. But making these states as good as possible, an ideal belt state is part of the game. If you do entanglement across the diagonal, you also can generate this state, but this is an early example here. You see that the quality is getting lower, and it is getting lower because the distance is getting larger, and this is why the interaction is getting larger. Your sequence takes longer, and decoherence kicks in. But at least you can generate these kind of coherences. All right. Now, an important thing is, and this is what we use to improve actually this entanglement, is that we have once again local nuclear spins around each electron spin site. And these local nuclear spins you can use for error correction and entanglement improvement. And this is the last thing I wanted to show you. Okay, so if we have our electron spin qubit, which I'm showing here on the top left corner, right? Then this is surrounded, of course, by the lattice, which is carbon. 1% of these carbons is carbon-13, and then to this carbon-13 you see hyperfine coupling. This is actually what we were using as memory qubits in our MRI experiment. So here I'm showing you a specific example where the electron spin is coupled to 3 nuclear spins: the nitrogen nuclear spin of the NB center and 2 carbon nuclear spins. And overall, you get then your quantum system is already gaining some complexity with in total 1, 2, 4, 6, 8, 10, 12 spectral components, right? If you now look, if you now measure one of those nuclear spin transitions or signals, and you do this as a function of time, you see that these signals undergo fluctuations. And these fluctuations are nothing but the quantum jumps of the nuclear spins close to the electron spin. The frequency of these quantum jumps depend actually on the hyperfine coupling, and they can occur from some seconds to minutes. So the important conclusion is here that you can do what we call single shot readout, and that is a very important prerequisite for quantum error correction. Now, well, this is just a different time trace. So why is it then that you can follow the quantum trajectory of these nuclear spins? Well, that's very easy to see. Actually, the Hamiltonian describing the combined electron nuclear spin system comprises electron parts. This is this part here. That's the dipolar spin-spin interaction part. This is the part of the electron spin interacting with the external magnetic field. This is the hyperfine interaction part, and these are all nuclear parts where the nuclei interact with the external magnetic field. Now, the important thing is the hyperfine part here, because it contains components which are parallel to the quantization axis of the electron spin, but it also contains components which are orthogonal. And these orthogonal components actually generate electron-nuclear spin flip-flops. And the magnitude of those, the impact of those on the quantum dynamics of the combined electron-nuclear spin system, you can control. And you control it by the external magnetic field. So if you exactly align your magnetic field along BZ, actually this part stays diagonal, this one becomes diagonal, and all of these parts here become diagonal. The only part which is generating a non-diagonal dynamics is actually this hyperfine component which contains this flip-flop part, and the rate at which this occurs you can suppress by increasing the magnetic field. So at high magnetic field, if you look at the nuclear spin relaxation time as a function of magnetic field, you see that there is this quadratic increase. This is what you expect from first order perturbation theory. So the larger your external magnetic field is, the slower the nuclear spin change their quantum state. And if you go to large magnetic fields, then actually the spin lifetime is approaching minutes. So for, I don't know if you have this here, yeah, so for 3 Tesla or so, you see the overall nuclear spin relaxation time is 4 minutes. So this is what we did here with this large magnet. Well, anyway, so this is how you can see the quantum trajectories, and that is very important, once again, for any kind of feedback algorithm in quantum computing. And the one algorithm I want to explain to you, I want to show you, and this is the final part of my talk, is quantum error correction. So what we do is actually, we encode one logical qubit, that's what you see down here, into 3 physical qubits. So all these 3 nuclear spins here actually now encode one logical qubit, say a logical one. Now, what happens if one of those qubits is undergoing a spin flip? This would be an error, say, right? This is very much like a family with kids. The kids typically rattle around, and once in a while they stand upside down. And now you do a measurement on this state, and what you do is a majority vote. So that's the classical basis for this quantum error correction algorithm. You ask, what is the average orientation of the quantum state? And the answer is, because you have these 2 adults and the one kid is standing upside down, is the average orientation is upside down, or the majority orientation, not the average, but the majority orientation. And this you take then as measurement result and correct the orientation of the qubit. Of course, if we would have 2 of your physical qubits undergoing spin flip, then you would have an error. And this, the number of qubits which can undergo an error before your logical encoding fails is called depth of the error correction algorithm. So here the depth is 1. This is the algorithm. This is how actually we run it. And you see it's already a sizable algorithm with a number of gates we do. I'm not going into the details of it, but as a matter of fact, it is very similar to a theme code type of algorithm. And in the end, this is the result. And that's about the last thing I want to show you. So here, what I'm plotting is actually the error probability. It's called process fidelity, but essentially it's the error probability of the 3-qubit register over the probability that a single qubit error is occurring. So here, what I'm doing is I'm deliberately changing the orientation of one of the qubits with ever increasing probability. So here, the probability to have changed the quantum state of 1 qubit out of 3 is 1. And here I'm looking at how efficient that is in actually corrupting my overall quantum state. If I do nothing, so no quantum error correction, actually then my overall error of the 3 qubits is exactly proportional to the single qubit error, right? If 1 qubit is oriented the wrong way, then the whole state is corrupted. But if I do error correction, then my error probability, that is the fidelity of my starting state, is staying constant. And it is this difference between this green curve and this blue curve, which is actually giving you the efficiency of the quantum error correction code. All right. So with that, I'm at the end of my talk. I guess we have some time for discussion. So overall, what I wanted to show you is that these spin defects in solids are very versatile quantum sensors for various parameters ranging from magnetic field to temperature. They are very good for imaging on micro and on sub micron scale. So spatial resolution we get in imaging of magnetic fields is on the order of 10 nanometer. They can be applied at very low temperatures, millikelvin temperatures, up to physiological temperatures. So they are interesting for material science and, for example, for biology. And in addition, they constitute quite good few qubit systems. How to scale them, we can discuss, but at least on the order of 10 to 20, 30 qubits, they are absolutely on par with all of the existing other hardware for quantum computers, with the one advantage that technically they are very simple. So the quantum computing thing I was showing you all occur or all have been done at room temperature. All right. So with that, once again, I'm at the end of the talk. This is the group in Stuttgart with various people from all over the world. Some come from India. Gopalakrishnan Balasubramanian actually bought the postdoc in the lab. He's now actually running a company here in Germany, trying to build a diamond-based quantum computer, just as an example. We get money from different sources, some of which is coming from the US, other is coming from Europe and from German Science Foundation funders. I thank all those people for actually their contribution and the money they put into our laboratory, and I thank you for your attention, and I'm happy to answer any questions. Thank you.
Thank you, Professor Jörg. Very nice. Thank you for giving us this fantastic overview. So the floor is open for questions. Yeah.
Hello, sir. So my question is regarding your vision to make a portable MRI. So how you are planning to obtain slices of organ as in a typical MRI? Because hot atoms are also used to detect the magnetic anomalies created by brain. So in your device, so how you are planning to get the exact position of the radiating spins?
Yes. Okay, very good question. Let me go back to that mock-up. That's very true. Where are we? Yeah, that's very true. That of course also thermal vapors are used as magnetometers, right? So there are two elements. Well, this is okay. There are two elements which are important to see. Oops, here we are. Here we are. Okay. There are two elements which are important to see. So normally MRI, so first of all, so MRI does not measure the magnetic fields generated by ion flow, that is brain magnetic fields generated by neural activity are on the order of femtotesla or so, and MRI is distinct from that because the signal is coming from nuclear spins, right? And typically that signal is not a DC signal, but it's coming at a certain frequency, as I was explaining, which is a Lama frequency. Okay, to get this frequency up, to get as high frequency as possible, MRI machines have these big magnets. Because in MRI machines, you use induction as a detection method, and induction essentially goes with the Lama precession squared in terms of sensitivity, right? The faster they spin, the larger the signal is. This is why you have these big magnets. Our sensors, and that is the same is by the way true for hot atom vapor magnetometers, the sensitivity of our measurement does not depend on the external magnetic field. So you can spare yourself the large external magnetic field. So how do you get spatial resolution? One way of getting spatial resolution is that this here contains a diamond chip. So this is a whole array of these NV sensors, each of which is measuring the response of different parts of the specimen underneath. This is how you get spatial resolution in the first place. You can add this up, and this is what we are doing with gradient coils, which are in here. And these gradient coils switch the magnetic field you use, and then you encode or you synchronize your data acquisition with these gradient coils. Now, so this is essentially how a conventional MRI works, but in this case, in a very much more compact way. Now, the restriction here is that that this works up until depth of, I would say, 3-4 centimeters. So it's a surface MRI technique. If you go below, then you would need coils which wrap around the whole specimen, which is not the case here. So to answer your question, spatial resolution comes from two facts. First of all, is a magnetic field camera, and depth resolution is coming from gradient coils.
Okay, sir. Thank you.
Other questions? Okay. Just one more.
Hi. One of the slides you have shown that the coherence value goes to negative.
Yeah.
So when your system interacting with the environment, it goes to 0, and that is fully mixed state. Further, it cannot be shared the information. So
Absolutely.
can you explain that the negative value of the coherence in information perspective point of view?
Yes, I can do this exactly. So yeah, thank you for the question. That's exactly the point, right? So coherence typically goes to 0, and then your system is entirely decoherent. Okay. Once in a while, we find that this coherence is negative, and that simply means that this is not an interaction between a quantum system and a classical noise source, but the quantum system and the noise source is getting entangled. Right, and then you have a fully coherent system, and then of course it can be in the unitary evolution of the system, the temporal evolution, it can get negative. This is it's a bit provocative statement here. It's called quantum decoherence, but essentially the system you're measuring and your sensor is actually getting entangled. That's the explanation of this negative coherence.
Okay, thank you.
There's one more there.
Hi, sir. My question is regarding the part where you showed producing Bell state through an array of NV centers.
Yes.
So I wanted to ask you, that is in the photon polarization basis, right? The Bell state? Or,
yeah, let me just go through it. Yeah, thank you for the question.
Yeah, but, oh, you were saying something.
Yes, just a second. It's not, it's not photon polarization, but these individual parts here are electron spins.
Okay.
And that's the entangled state of the electron spins. So this is spin up, this is spin down.
Okay, so what is the map that you're showing there? Is it fluorescence or something else?
Yeah, we read out the quantum states by fluorescence, but the map is actually a tomogram of the spin state. Okay. Right?
Not that map, so the left map, the contour.
This one here, this one here. Oh yes, that's fluorescence intensity. So these color centers, they emit fluorescence when you excite, and this is essentially a fluorescence intensity map. Yeah.
Okay, so how do you, I mean, there has to be some interaction between these two emitters to get the Bell state, right? So how do you, is there a way to control the interaction, and what sort of an interaction is it?
Yes, absolutely. Sure. So the interaction between these two emitters here is not by photons, but it is by their magnetic moment.
Okay.
So the two systems have a magnetic moment, right? And their separation is 30 nanometer, and it is a magnetic dipole interaction.
Okay, so basically by applying a magnetic field, I can also control the interaction some way? Or?
Yes, yes,
Okay.
absolutely. Yeah, it's a spin triplet.
Okay.
So right, it's not only spin up and down, but it is spin up, spin down, and then it's a mixture between up and down, and this has zero magnetic moment. And so when you are in this state, you can switch off the interaction. So it's a switchable interaction.
Okay, okay. And so one more question. So how many pairs of these emitters show, I mean, is there an idea as to how many pairs show this sort of, produce this entangled state basically?
Yes. So in this, yeah, very good question. So in this arrow, we can entangle all of the 9.
Okay, okay.
So right, so you can make a 9-party VS state if you wish. Yeah.
Okay. And sir, one last question. So for the NMR imaging part and also the thermal map that you had shown, what are the time scales in which you took the maps?
Okay. So the cellular image also roughly took, I would say, 10 minutes.
Okay.
And the thermal map, this is done within seconds.
Okay, so I'm not sure about this, but I've heard that these biological cells, they mutate very quickly. So
yes,
was there a way for you to avoid that during taking the map?
Yes. So as a matter of fact, the image was taken on what people call a fixed cell.
Okay.
So you can actually inhibit or slow down the motion of the cell quite drastically. Yeah.
Okay, okay. So some sort of a liquid matrix or something to
something like this.
Okay.
Yes, it partially polarize the interior of the cell.
Okay.
Polymerize, and this makes it stiff and
got it. Thanks.
Okay.
So any other questions? So I have one last question, maybe Professor Jörg. So what is the reliability of creating these emitters, in this very precise nature? Like, what is the, conversion efficiency?
Okay, yeah. Very important thing to discuss. Actually, the yield, we call it yield. So the color center generation per implanted ion very much depends on the way you do it. So what we do is we implant the ion, and at the same time we look at the generation of the color center. So you shoot in the ion, at the same time you illuminate the spot with a laser, and you stop ion implantation when you have a color center formed. So if you take this as a measure, the probability is close to 100%. Sometimes afterwards you find that your defect center is not good, low coherence time, for example. If you do not do this kind of online control, then you need to shoot in 10 ions to get one NV center. So the yield is 10% per implantation spot.
I see. Okay. Okay. So thank you very much, Professor Jörg. If there are no further questions, there's one more question there. So we'll just take one last question from a student.
Hello.
Yes.
Yes, sir. So the chip design that you have shown, the 3x3 NV center chip that you have shown. So one question is, are these single centers?
Yes.
Okay. So the distance between these centers, if it is somehow fixed, does this somehow give us a limit on the size of the chips that we can use, or the size, the distances between them is just arbitrary, or is it like, is it going to change? Or can it even change?
No, I mean, once you have generated the chip, the distance is fixed, you cannot do anything. You can change the interaction by quantum control techniques. You can modulate the interaction up to a maximum amount given by the distance. I would say in our lab, the maximum entangled state is in the 3x3 registers. If you would have larger registers, then the distance would be so long and the coherence times would be in the end limiting you that you could not generate larger entangled quantum states unless you use the nuclear spins, right? So the nuclear spins are a very valuable degree of freedom. So you have a handful of nuclear spins for every electron spin, and you can use this actually to multiply the size of your register.
All right, sir. Thank you.
There's one more question.
Okay.
Hello, sir. This is related to my last question. So in the portable MRI, so there is no need of high magnetic field to first align all the atoms?
No, there is not.
Okay.
Yeah, no, there is not. The point is, yeah, no, there is not. So what you rely on, so you do not need to align the nuclear spins to get a larger signal. That is not what you need to do. If you have a small observation volume, then what you are actually measuring is a statistical fluctuation in the magnetic moment, which is getting larger than the thermal polarization. And this is what we are using.
Oh, there is a few more questions I can see, Professor Jörg. It's very interesting.
Hello?
Yeah.
Sir,
Okay, yeah, go
this
ahead.
so the 3x3 NB-centered size is 0.1 micrometer, that's 100 nanometer. So is these are confocal microscope images or other technique?
No, it's a super resolution image. It's a ground state depletion image. So it's STAT-like, simulated emission depletion.
Okay. Any other questions? Okay. If not, let's thank Professor Jörg for this fantastic talk and an overview. And thank you for the 2 talks, in fact. And so we have a little gift for you, which we cannot give you physically, but we'll ship it to you. So please send us your address. Thank you very much again, Professor Jörg.
Yes. Yeah.
Thank you.
Yeah, thanks for attending and the question and the discussion. Okay, hope to see you anytime soon. Bye now.
Thank you.